Good morning, everyone. Welcome to this second day of the heterogeneous programming with SYCL workshop that we as ENCCS are organizing together with IT4I and NRIS. So today we're gonna talk about expressing parallelism, and as Stu mentioned a little bit before, when not so many of you had connected yet, we will try to have breakout rooms that last a bit longer because the exercises are a bit more involved today. So I won't be talking as much as yesterday, which I think is good because you get more time experimenting with the exercises on Carolina. So 2 notes before we start. So if you clone the workshop repo yesterday, and I put a P too many here in the hackmd, update your local copy because I made a few small changes reorganizing, moving some of the exercise folders for tomorrow. So here are the list of commands that you should, the Git commands that you should type to do so. So stash your changes, do a pull -- rebase, and then you can pop the stash to get the changes that you made yesterday back. And to the repository, I also added a copy of a submit script to the queue on Carolina. So this is basically the same, it contains the same stuff that is at the top of the hackmd, but now it's already in the repository, so you don't have to copy paste from hackmd every time. You can just copy this sample file, just change the name of the executable that you want to run, and it should work. If it doesn't, let me know. So after this general information, of course, remember that it's preferable to ask questions about the materials on the hackmd instead of the Zoom chat, because there's a record for everyone to look at questions that have been asked and answered before, that we will keep online. So if you want to refer to it even after the workshop, it will still be there. A thing that cannot be said of the Zoom chat. So just remember that. Okay. Short recap of what we saw yesterday. So there was kind of a whirlwind introduction to what is SYCL and why is it interesting to learn this other programming framework for heterogeneous programming. We talked mostly about memory management yesterday. So what are the options for reclaiming memory from the GPU or the CPU memory hierarchy using SYCL? How do we manage data movements, or how the runtime knows how to manage data movements for us? So today is all about, in the first 2 parts, how we can use now these buffers that we've allocated on the device to express parallel kernels. Okay, so how to express parallelism with SYCL. So yesterday, if you remember, in one of the in the Q section of the training, I mentioned that there's 3 ways of expressing parallelism with SYCL, but we didn't dive into them because that would have taken much more time that we allocated, and we have the whole day today to do so. So we talked about so-called basic data parallel kernels, ND-range parallel kernels, and hierarchical parallel kernels. So today we're going to see in this section the basic data parallel kernels, how do we express them and when they're appropriate. And in the next section, ND-range parallel kernels. As I also mentioned yesterday, we're not going to talk about hierarchical parallelism in SYCL, and that's because it's part of the standard, but the implementations so far are not optimal. So many compiler implementers have added their own extensions, which are not part of the standard yet, so it's something that you should probably not rely on quite yet. So as I was saying yesterday, we saw what are the pieces that make up a SYCL program. So the queue is the central abstraction that one should always keep in mind. And through the queue, we saw that we can manage the submission of parallel work, but also, if necessary to do so explicitly, memory movements. We saw that within the queue, we have a command group handler if we want to manage operations that are a bit more complicated than just launching a parallel 4. And within a parallel 4, we launch it by giving a range of execution and a kernel. So a function that we have usually expressed as a lambda function that describes how the computation on each of the elements in the range should appear. And finally, we looked at buffer and accessors for memory management and unified shared memory. So the way of expressing parallel kernels we didn't really discuss. We had a short look at how things could look like, and the exercises did show something, but we don't know exactly the details. We showed that we can distribute one-dimensional work on a one-dimensional array using a range 1 object type and an ID 1. And I saw in the hack and did that there were questions. What is this ID object? What does it do? How does it work? Today, all these questions should hopefully be answered. But before diving into that, let's have a bit of a look at general concept. So the difference between data and task parallelism. So because these are the kind of the two kinds of parallelism that we would like to exploit in our programs. So data parallelism, and here I have this little picture that was made by our colleague Artem for a CUDA workshop. So we assume that we have a bunch of data that is in this case arranged in a vector, and then we have a function func1 that can operate on each element in this array separately and do something on it. Okay, then with data parallelism, it's by definition this kind of distribution of work where a function can operate on elements of the same array separately from each other, such that I can spawn multiple instances of the same function, each one taking care of just one element in the array and producing one output element in the whole array. So when we talk about task parallelism, instead is when we can execute two such functions, for example, func1 and func2, that both are able to work on a different array at the same time. So to make this probably slightly more clear, a common example of data parallelism is when we want to apply a filter on an image. And an image is represented as a set of pixels, and a filter can work on each pixel separately in many cases. And in this case, we can call the filter function to work on each of the separate pixels so that we can process the whole image all at once instead of having to kind of not be able to exploit this kind of parallelism. So we can this is the ideal situation in which a GPU can work, because the same instruction sets, in this case, the instruction set in the func1 data in the picture can be executed on multiple threads, and each thread takes care of a bunch of elements that are separate from each other, that have no dependencies with each other. An analogy for task parallelism is when there's multiple people in the kitchen, or you're trying to prepare a recipe that requires multiple steps. Of course, if you are alone in the kitchen, you will have to do each of the steps sequentially, one after the other, in a specified order. Whereas if there's multiple cooks in the kitchen, you can distribute the work of, I don't know, slicing the vegetables or cooking the bread across different cooks, and things will be done faster by virtue of the fact that you can schedule these tasks to execute concurrently. So how can we take advantage of these two different kinds of parallelism with SYCL? So the task parallelism, which in the analogy I just used means basically assigning different kinds of work to different cooks in the kitchen, is largely delegated to the runtime itself. As I said yesterday multiple times, SYCL is an asynchronous programming model, which means that once we have a description of the tasks to perform. We can arrange them in a graph, and the edges of this graph describe the dependencies between the different tasks. And whenever the runtime knows that some tasks are independent from each other, they can be scheduled to execute concurrently, so at the same time. So these would be like one thread slicing the vegetables and one thread cooking the bread, for example. So what is left for us is to basically exploit this data parallelism, and this is done through the parallel_for function that can either be called on the queue object or on the command group handler object. So yesterday we saw that the parallel_for accepts two arguments. The first argument is an execution range, and the second argument is a kernel function that we saw can be expressed either as a lambda function or as a function object. The difference between the different kinds of parallel_for, I said there is a basic, range, and hierarchical, is basically in the way that this execution range argument is passed in. So the basic one is to be used when execution is parameterized over 1, 2, or 3-dimensional range object. And we call it basic because we don't have much control on how each of the data parallel tasks is scheduled. Okay, so we don't have a fine level of control over low-level features of the scheduling of the parallel_for. For example, we don't have control over locality of the memory access. So if that's something that is needed, we should go look at ND-range parallel kernels. And the signature of this simple parallel_for is as follows. So as you can see, it takes a range with a given dimension, can be 1, 2, 3, and then the rest of the arguments is passed in as variadic pack of arguments. So in principle, there can be multiple arguments that come in. Yesterday we saw that we only pass a single lambda function for the kernel. The second flavor of parallel_for is so-called ND-range, and ND stands for n-dimensional range. So again, execution is parameterized over 1, 2, or 3-dimensional, 3 dimensions. But instead of using a simple range, we use so-called n-dimensional range objects, so ND_range. So the two flavors of parallel_for do look quite similar. Even if you look at the function signature for launching this parallel_for, you will see there's a range object first and then the rest of the arguments, which in our case will be a lambda function or a function object. However, the ND-range is defined in terms of multiple ranges, and we will see that in the next section, so that it allows you to group instances of the kernel together, meaning that you can separate the whole set of work items into smaller groups, and within these groups you have further guarantees on synchronization and scheduling, and you have also more flexible control over the locality of the memory access and the mapping to actual hardware resources. So if you need to use, for example, a local shared memory, you would need to look into writing an ND-range parallel_for. And the final one, which, as I said, we will not discuss, is so-called hierarchical parallel kernels, which allow you to nest kernel invocations. So these can offer an interface that is a bit simpler than ND-range parallel kernels. But as I said, this is a fast-changing area in the standard, and your mileage may vary with respect to the SYCL compiler implementation that you choose. So how performant it is and how well supported it is. So if you're interested in this, you should keep an eye on the standardization process and what the SYCL implementers are doing to support this feature. So something that should be kept in mind when we talk about parallel_for, despite the name, it includes the for, is a data parallel kernel is not a loop. So when we launch a kernel through a parallel_for, so what the runtime will do will instantiate the same operation that is described in the kernel function, so in the lambda function that we pass in, over all the data elements in the execution range. So the execution range maps to the data array, and the runtime will instantiate one version of the kernel for each of these data elements separately. So these instances can run in parallel, but it's not necessary that they run in lockstep. So it's not guaranteed that when one of these instances advances, it consumes its data and produces some result, the next instance will do the same at the same time. So the data parallel kernel construct, even though the name includes 4, so parallel 4 is not performing any iteration. So it's a descriptive abstraction over the concept of a loop. So it's left to the execution model and the runtime to schedule this parallel for such that it performs the operation in a parallel fashion, but it's not necessarily achieved through a loop. Okay, so this is something to keep in mind, because it also influences the fact that how we access shared local memory and so on, and synchronization, which we will see in the third section of today. So after this introduction, let's finally look at basic data parallel kernels. So these are most suited for embarrassing data parallelism. So basically the perfect case where we know that each kernel instance can operate on one instance of the data separately from all the other instances of the data. So if we think of the blurring filter that I mentioned before, when discussing data parallelism, this is exactly the kind of parallel for that you would write for that example. So the first argument to the parallel for is the execution range. Again, this is a range object that can be 1, 2, or 3-dimensional, and that's given in the template argument that the range object accepts. So the range is a grid of so-called work items. Okay, so I have this little figure here. So assume that we have a 2D range with dimension, how many blocks are it? 7 by 7 here. So this range 7 by 7 is a 2D range. And each of these little squares is an item object. So an item, again, is templated over the dimension. In this case, each of these blocks in the figure is an item 2 kind of object, and each item has its own identifier, its own ID, which is also templated over the dimension. So range 2 is made up of item 2, and each item 2 has a unique ID 2 that basically gives you the coordinate of the given item within the execution range. So this element here in orange, it's an item 2 that has ID 0, 1, 2. Oh, sorry. 0, 1, 2 and 0, 1, 2, 3. Okay. And the same for the purple highlighted element. It's an item 2 with an ID 2 of 4, 2. So since this is C++, the ordering of n-dimensional ranges is row major. So the last dimension in the range is the contiguous one. So which is something that we should keep in mind, but mostly for later when we talk about n-dimensional ranges. So the kernel function that we pass a second argument to the parallel for can either accept an ID or an item type. So yes, all the kernels that I showed in the examples were accepting just an ID object, but we can keep it a bit more general and make it accept an item. So what is the difference between these two ways of writing the kernel? So when do we want to use ID and when do we want to use the item? So the ID knows about the individual kernel instance only. Okay, so the runtime will schedule the same kernel to be applied to all the elements in the range, so to all the items inside. But if we use the ID to parameterize, the only information that is passed down to the kernel is where in the range we are located. Okay, so for the example above, if we parameterize our kernel over an ID, then we would just know when we're executing this 2, 3 element that we are at position 2, 3 in the range of execution. So this is useful when you don't care much about what the other items are doing in the kernel. So in most instances that we were looking at yesterday, this is more than fine. So if we want to just assign a given value to all the elements in an array, it's perfectly fine to just index based on the ID object. And we saw also yesterday that if we're using buffer and accessor, the ID type object can be used directly to index into an accessor without having to unwrap the numerical value of the index. In this case, it would be 2,4 in the example that I was showing before with that range. Well, if we're using USM is pointer-based way of doing things. So then we would need the numerical values. So we would need to linearize the index if we had a 2D or 3D range, keeping in mind that it's row major. So the item not only knows about its own ID, so where it is located in the matrix, but it also knows about the global execution range. So meaning where, how the global execution range is structured. So how many dimensions there are there. So you can get, once you have the item, what you want is to get the ID, and for that you would call the getID function. And once you have the ID, you can use it to index into the array. So this is useful, for example, if you have to work with multiple buffers and accessors, and you want to, for example, get an index that is not exactly mapping to the one of the current item. So now we will see, we have a breakout room now with the matrix multiplication exercise, and we will see that here when we are indexing on the A and B matrices on the right hand side, the operands, it will be more useful to use an item than an ID. So yeah, so this is all for the basic data parallel kernels. So what we can do is open breakout rooms and try to do this exercise. So today I've put in, yeah, so I think it's more or less self-explanatory. I've put longer explanation on what to do in each of the prompts. Same as yesterday, so if you want to just skip over to the solution and work your way back from that, you're welcome to do so. Okay, let's move forward. So it was pointed out in the HackMD that what I said about write only for the C accessor, that's obviously wrong, because we are updating, we are accumulating on top of C with plus equals operator. So one should use read write, but I think it's Andre replying that hipSYCL doesn't make a difference between read write and write only at this point. So, but okay, let's move forward to the next section, which is, put it in presentation mode. She's talking about ND ranges. So the range based parallel 4 construct, also called basic data parallel kernel, can be used, as we've seen, to express parallelism. It's not the most flexible kind of construct because you cannot control some of the low-level details of the execution. So is there a way to have more power, more control over how these things are scheduled? Yes, there is, and it's through this n-dimensional range data parallel kernel. So with the previous construct that we've seen, we map problems that are in 1, 2, or 3 dimensions to the available hardware, and the way this mapping is achieved is more or less decided by the runtime for us. So as I was saying, the semantics of this range class is quite limited because we have access to where in this matrix of items we are with the ID object, or where the item is in the whole range with the item object, but we have no way of expressing notions of locality with this kernel. So we cannot, in a way, have control over memory locality, memory accesses, and so on. So if we look again at the matrix multiplication exercise, this is kind of obviously if you squint. So each work item in the range addressed one element in the output matrix and would load a full row of the A matrix, the left operand, and the full column of the right operand. So while the row of A is contiguous in memory, the column of B is non-contiguous because we have to do a full skip over the row to read the whole column, okay? This loading of both the row of A and the column of B happens multiple times, okay? So whenever we get to an item, we do a full read of a row, a full read of a column to update the one element in the C matrix. So this is, of course, kind of wasteful because one of the two operands we have to read in a non-contiguous fashion, and we have to do that multiple times. So there are ways to optimize this, but we need this ND range construct to do so. So I anticipated, I told you before that they do look a bit similar, ranges and ND ranges, but because they kind of express the same concept of a 1, 2, or 3 dimensional iteration range, if you wish. And the ND range itself is templated over the number of dimensions, but the constructor looks markedly different because instead of accepting just the integer dimensions in extents in each of the dimensions, it accepts two ranges. One called the global range and one called the local range. What do this means? What does this mean? Why do we send in two ranges to construct one single n-dimensional range? So the global range gives the total size of the ND range. Okay, so in our example, it would be the full n by n matrix, so to speak. So the full n by n range 2 that we want to map to the output matrix C would be the global range of the n-dimensional range. And then the local range is the size of a work group. So before we had a whole 2 by 2 matrix of work items that was just that. So we have this bunch of work items that are grouped in a range. With the ND range, we can decide to have this bunch of work items, so n by n, and then subdivide it into smaller bunches of work items, which are called work groups. Each of the work groups can further be subdivided into subgroups. These are always one-dimensional, and it's an implementation-dependent feature of SYCL, and we will have a look at it tomorrow, how to use subgroups. So I have prepared this little figure to help you understand how this bunching of elements works. So we have the ND range here at the bottom. In this case, it's a three-dimensional ND range. And again, this is stored in row major order. So the last dimension is the contiguous one. And this is an 8 by 8 by 8 ND range. So 512 work items. Each of the little cubes is a single work item. So the global range is 888 when we declare it to pass it to the constructor. And then we further subdivide it into 8 work groups. Okay, and each work group is of dimension 4 times 4 times 4. So that would be a range 3, 4, 4, 4. And finally, there can be an implementation-dependent further subdivision into a subgroup. So the subgroup is always aligned along the contiguous dimension of the work group and is of a size that is implementation-dependent. Okay, so it can be, for example, on this NVIDIA hardware that we have access to is of size 32, so it comprises 32 work items. And each of the work items is, as I said, is one of the little cubes. Okay, so we have basically a whole range of work items that we decide to further subdivide it into smaller work groups. So how does this help us? So the work items in an ND range, just as for the basic ranges, represent instances of a kernel function. So when the runtime decides to schedule a kernel given an ND range, it will map it to, it will give it to a work item. Okay. As for the basic ranges, each work item cannot communicate or synchronize with each other, and they are scheduled for execution in any order. So this is important, that we are not guaranteed that the execution of work item I comes after that of work item I minus 1. So the fact that we bunch the whole work items into smaller work groups is what is brought to the table when we use n-dimensional ranges. The fact that these work items are grouped together gives us some more programming tools, meaning that each work group, so each bunch of work items described in the local range, has access to work group local memory. So this memory can be accessed by any work item in the work group, and how this memory is made available depends on the hardware that you're using and the SYCL implementation. So it is an implementation detail. So at the group level, so within one whole work group, we can use barriers and fences to synchronize all the work items in the group. And we can also use so-called group level collective functions for communication between the work items in the work group. So for example, we have broadcasts, which we will see in the episode on subgroups tomorrow, or collective functions for computations, for example, a scan or shuffles and so on. So all the work items in a work group are scheduled concurrently to a single compute unit. So there can be many more work groups in an ND range than compute units in the hardware. So this is not a problem, because it's usually fine to oversubscribe the hardware, so to submit more work than what the hardware can handle at one given moment. And also we avoid to kind of tailor the code to the specific hardware. If we just always, because otherwise you would have to know beforehand how many compute unit the given hardware has, and that's something that we cannot write in a generic and portable fashion. So work items are in a work group are not guaranteed to make progress independently, and this is good because it gives the runtime enough freedom to schedule things to execute as efficiently as possible. Because if the runtime were to guarantee independent progress, then it would basically need to serialize most of the time to make sure that the code would run correctly. So in an ND range, parallel kernels, instead of using just the item or the ID object as argument to the kernel function, to the lambda function that we pass in as kernel, we use so-called ND item. Okay, so this is generalization of the item type. The difference is that whereas the item again gave you access to just the one ID in the range, the ND item will give you access to two IDs. The ID in the global range, so in the whole bunch of work items in the ND range, and the ID in the local range, so within the work group. So you can, of course, work with get global ID and get local ID methods to get the ID within the whole ND range and within the work group. But it is often better to first get the group to which a given work item belongs with the get group function. And tomorrow we will see that there's also gets a subgroup if we work with subgroups. And then from the group, you can probe what the ID is with methods on the group object that is returned from get group. So this went incredibly fast with respect to the previous section. So we're gonna look again at the matrix multiplication exercise and try to make it a little bit less naive. And by a little bit less naive, I mean that we can optimize the memory accesses a little bit if we have more control over how the work items are bunched together. So how does this work in a like higher level fashion? What should the algorithm do? So before we saw that to compute one element in the C matrix here, for example, the green one that I'm pointing to with the mouse, we would load the one full row of the A matrix, contiguous in memory, and one full column of B, non-contiguous. And then moving on to the next element, again, we would load the full row and then column and so on. And this would be done multiple times, which we saw would have, it's not the most performant way. So what we can do now, we can have a global range that still maps to the whole result matrix C, and then subdivide it further into work groups that map to regions in the C matrix, not the whole thing. So the local range would be smaller than the global range. So what does this mean? It means that whenever we are in a work group, we can reuse the data that was loaded to compute elements within the same work group. And this is what I'm showing here with the orange color and the orange shading. So assuming that the whole range, the global range is 8 by 8, and that the local range is 4 by 4, we basically subdivide the full matrix into 4 smaller submatrices. And within each work group, whenever we compute one of the elements here, we load the 4 rows of the B matrix and the 4 rows of the C matrix, so that we can reuse them to compute this whole area instead of loading them over and over again. So this splitting is maybe a bit more optimal, but probably not exactly the best. Of course, I have this comment here that I also had in the description of the previous exercise. If you need to do any BLAS or LAPAC operations in your code, don't write your own, use libraries, because for sure they're more optimized than what you could possibly think of, because there's been a lot of people working on it for many years. So, okay, this is what I would like you to work on in the next breakout room. Again, the start of the exercise is the same. Create a queue, create the data buffers and fill them with random numbers again, and then create buffers as needed and submit work to the queue. This time you want to use an ND range parallel for loop. And as shown before, what you want to do is to create the global range that maps to the whole result matrix and the local range that maps to subgroups in the matrix. So something that I think I skipped before, the extent of the local range in each of the dimensions needs to be an exact divisor of the global range in the same dimension. So if the matrix is, as in this case, I think 256 times 256, you cannot have a local range that is 15 by 15, okay? So in this case, I set it to 4. I think the size of the local range, but you can experiment with larger sizes. Everyone? So I was looking at this website that I think Andre posted in the HackMD. So this is really useful if you're wondering on specifics of class definitions and constructors and so on. I usually refer to the spec, but the specification can be a bit drier in detail, so it might not be as explanatory as this other document. So if you ever wonder, you should bookmark this website. It's really nice. It's also searchable. If you find mistakes, you can actually open an issue on GitHub and suggest modification to fix that. So that's really nice. So this said, while everyone was in breakout rooms, there was a power outage here at the ENCCS headquarters, so we had to kind of set up everything anew, but that was fixed during the break. So a quick peek at the solution of this, was it 02 and the range? Yeah. So thinking that I would fix something in the exercises, I copy pasted the natural programming mistake. So here this inner loop should be auto k and not just decl type, and but I posted it in the hackmd again. So so the beginning of this proposed solution is the same as for the range-based parallel 4. So for the basic flavor, the difference is that, okay, here we declare the row and column dimension of all these matrices n, and as we said, this will be the global range of execution that maps onto the result matrix C. Then within the new scope, I define a local range with size B of 4. So this is pretty small. We could have tried 16, for example. And then what do? So we declare the buffers again to A, B, and C matrices. And these are mapped onto ranges 2 of n by n size. And within the command group handler, so within this lambda function that we submit to the queue, we declare the global and the local ranges. So the global range is n by n, and the local range is b times b. So we have this 256 times 256 matrix, and we decide to split it up so that there's work groups that handle 4 times 4 grids of work items. So the parallel 4, now we pass an ND range as first argument, which is built up of the global and local ranges that we've just declared. And then the lambda function now accepts an ND item 2, okay? So now that we have this item is aware of basically its position in the global range and its position in the local range. So within the work group and within the bigger grid of work items. So here we just decide, I mean, for simplicity, since I'm not gonna do anything very complicated, with the work group, I just probe the item IT for its global ID. The global ID, it's of type ID2, so it wraps 2 integers, one for the index, row index, and one for the column index, 0 and 1 respectively. And then I write my loop, inner loop again as before. So this doesn't look that dissimilar from the basic parallel 4 launch. The thing is now that since we're using splitting the work further in subgroups, we have given the runtime more information about how the memory access should be organized, and this should basically let us get away from the very naive implementation where we reread the same data over and over again. There's still data that gets reread multiple times. Of course, this is, as I said, is not the most optimal way of organizing this computation. So to see how we can have even more fine-tuned control, we need to learn about how the runtime generates the task graph. So about how the nodes in the task graph are generated and how the edges are generated, how these things are connected, and how the runtime makes its decisions about scheduling the tasks. And finally, how we can synchronize within parallel 4. So this is these are the topics of this section. So we know from yesterday that again the queue is the central object, one of the most important objects in the SYCL standard that lets us map work to device. And what the runtime achieves when we have this submission work to the queue is generate the task graph. So this is composed of nodes and edges. Nodes are actions to be performed on the queue, and edges are dependencies between different nodes. So as I said yesterday, the task graph has a well-defined direction of execution. So there's a start and there's an end to the execution, to the control flow of the program. There are no self-loops, there are no self-dependent tasks. So it's so-called DAG, directed acyclic graph. So whenever there's an edge connecting two nodes, that describes the dependency, which means that there is it imposes an ordering what should happen before. So if task A connects to task B, task A should happen before task B can start. So usually it's not necessary to directly work with the task graph, so directly influence how the runtime produces this abstraction for us. Indeed, there is no direct object in the SYCL specification where we can probe how this task graph is made. And why it is not directly necessary to work with it. So if you use buffers and accessors, as we've seen yesterday, the runtime has enough information to directly produce all the edges and all the nodes in the graph already. So it knows when to do allocations, when to do memory movements, which memory movements are dependent on which allocations, and so on. And also which kernels depend on which buffers through the use of the accessor API. Similarly, when we use USM with implicit data movements, that's also something that the runtime can understand and produce correct code for. When you're using explicit data movements, you are then in charge of the scheduling. So we've seen yesterday that if you do a copy or an allocation, these are also asynchronous. So you should put .wait. You should call the wait method on the queue to make sure that the action happens before you move forward to use the memory that you have been allocating or moving. So interaction with the task graph might, however, still be necessary, even though we don't need to get into the details of ordering stuff and making sure that everything makes sense. It might still be necessary to interact with it to get performance. So the queues, we haven't given any detail as to how the queues kind of decide how to order the tasks that we submit. So in this figure, I show two possible task graphs that the SYCL runtime might produce for our application, depending on what the application is doing, obviously. So these are so-called linear pattern when we have 4 tasks that each depend on each other in sequence. So before we can work on task D, task C needs to complete, task B in turn needs to complete before task C, and so on. And then we have this called Y pattern, where we have a task C that depends on the execution of 2 previous tasks, but task A and task B do not depend on each other. So in principle, the runtime can decide to schedule A and B to execute concurrently. And when they're both complete, it can start working on task C and then finally on task D. So the SYCL queues come in 2 flavors. So what is called out-of-order queues and in-order queues. So out-of-order queues, they are the default. It means that we're not guaranteed that tasks that are submitted in the code after each other will execute after each other. So it means that here we leave to the runtime the opportunity to organize tasks in a Y pattern, meaning that if I call q.submit with task A before q.submit of task B, not necessarily the 2 things will run after each other, but the runtime can reorganize if they do not depend on each other. And the next kind of queue is so-called in-order queues. So these are not the default. You need to initialize the queue with the corresponding property here. So property queue in order. And here, the runtime assumes that whenever you submit things, the order in which you submit is the order in which they should execute. So if you use an in-order queue, no matter what the dependencies between tasks are, you will always get a linearized task graph. Okay, so this might not sound incredibly exciting or useful, but it might be useful in case you want to, for example, debug an application. Then you can always modify the way you declare your queue to be in order so that you are ensured that the submission of tasks in a specific order in your code will result in exactly the same task graph at runtime. So this is not the default, of course, because it might impact performance a lot, but it's also something that you should keep in mind that can be useful, as I said, for debugging. So out of order and in order queues are kind of the most basic level of influence that you can have on how the task graph is produced. But not all the time you need to linearize everything that is submitted to the queue. Sometimes, again, for debugging, you just want to make sure, for example, that one task completes before another, just to analyze how what's producing the bug, for example. So that can be done. You need to use events, okay? So SYCL as an events API, and then you can obtain an event from a submission to the queue, for example, and then wait on that specific event instead of waiting on the whole queue, okay? Because in the examples that we've seen so far, we submit one action to the queue, and that's it. But if we submit multiple actions to the queue, instead of waiting on the whole work in the queue to be completed, we can just decide to wait on one of the various submissions that we've pushed in the queue. So in order queues, as I said, this is the basic way of working. Everything in the queue gets linearized into a linear task graph. So through accessors on buffers, you can describe dependencies between different buffers based on how you're going to use them within the parallel 4. This is more flexible than in order queues, but still it's something that works within the realm of memory allocations and memory management, memory movement, and probably you want to express some other kind of dependency here. So this is where the event-based approach comes in, because this is the most flexible way of doing things. Both methods on the handler class and the queue class, as I said, are asynchronous. So they return immediately an event, an object of type event, while the result of their execution might be produced at a later time. So when you have an event, a hand, or even a vector of events, you can decide to use this depends on method to express to the runtime that whatever happens next needs to wait on the previous events to complete before moving forward. So let's see how we would express this Y pattern. So if we use an in-order queue, which is what we were saying before, we can have a task A, then submit the task B, task C, and task D at the end. The in-order queue will just disregard the fact that A and B can execute independently because they're filling two different arrays, and will execute them in the order in which I'm writing the code. So first A, then B, and so on. So this doesn't really express the Y pattern, it just linearizes it. So if we use accessors, how would that work? So now I'm assuming that I have buffers for A and B declared already for the arrays that I was showing before. And then task A would look like this. I submit to the queue a parallel 4 in which the accessor on A updates its element with a given value. Then task B does the same for the vector B. Then task C sums the two, and task D is a single task that just updates the value of of one element in the array. Okay. So this looks again like a linear chain of submissions in the code, but the runtime can read through, can analyze this code that we've written and decide that task A and task B can execute concurrently, so that they don't need to wait on each other. And if we use the events API, So let's look again at the initial case where we have USM allocations of A and B vectors on the given Q. And then instead of just calling q.parallel4, now I capture the return value, which is, as I said, an event. So auto E1 equals q.parallel4 is an event, which we can wait on. So we can call E1.wait to make sure that the results of the parallel 4 are available in the A array, for example. So task A and task B are declared like so. And now we have these two events here. And they can be executed concurrently because they do not depend on anything that was happening before. They just depend on A and B, but they've been allocated already. And then task C sums the two. And here I call the parallel for now with 3 arguments. So first the range of execution, because I'm going to address both the A and B array, which are one-dimensional, and then a vector of events. So to run E3, both task A and task B need to be completed. So I have to wait on E1 and E2 of these two events to be done. And then finally, my kernel function here. And then for task D to proceed, E3, the task C, which generated event 3, needs to be completed. So I call q.singleTask, waiting on E3, and submitting this kernel here. So with events, we have total control on how to organize the task graph. And they can be useful even if you're not trying to influence directly the task graph, again, as a further control point. For example, if you need to debug the concurrent execution of tasks. Because you can always capture the event and then wait on it explicitly if you wish so, or just capture the event and then not use it or what have you. So let's talk about synchronization now. So we've seen so far how we can just wait on a queue. So that's an obvious synchronization point. Whenever we wait on the queue, like execution stops until everything that was submitted to the queue is completed. So that's one way of synchronizing between host and device. And in CUDA and HIP, this is usually achieved when you try to do device to host copies. So whenever you have some results done on the device and you want to copy them back to the host, that's the obvious synchronization point between the two. So in SYCL, we have a few options. So we've seen the wait method on the queue object. We have used it basically in all our examples because that's the easiest thing that we can do without having to discuss the events API, but it's also the course's synchronization level. Because as I said, everything that has been submitted to the queue up to that point where we issue the wait command needs to complete before we can move forward. So we might have submitted many actions to one given queue, so to one given device for execution. And if we wait on it, that means that we will block until everything is each and every one of these actions is completed. So probably not always ideal, especially if you are working with a very large scale application that might have thousands of actions submitted to a queue at any given time. So for final control, we have the events API that I shown before. So whenever you submit something to the queue, either with parallel for or with queue submit or with single task, what is returned is an event. And then you can wait on the single event with e1.wait, like so. Or if you collect a vector of events, as in the second example, you can call the static method in the event class to wait on a vector of events. So here you're waiting both on E2 and E3. So one other method is by the use of host accessor. So this is even finer level of control than the events API. Why so? So because they define a new dependency between a task in the graph and the host. So such that the execution of the task cannot proceed past the construction of the host accessor. What do I mean by this? So let's look at this example. So I have a buffer A over a range of 256 elements. So I'm using the constructor that does not allocate memory or does not refer to memory that has already been allocated. So this just represents a vector that is 256 elements long. Then I open a queue and submit some work to it through a command group handler. I create an accessor, and then I submit a parallel for to fill all elements in this A array with 1.0. So what happens here is that the runtime will allocate memory for me and then fill it in a parallel for loop with this 1.0 value. I can put more elements in the queue here to my leisure. And then what I want at the end is to have a copy of this A array that was initialized and I worked on it on the device. I want a copy of it back on the host. So to do so, I can declare so-called host accessor and look that the host accessors can be declared outside a command group handler, unlike normal kinds of accessors. And I build it, HA, I construct it from the A buffer. So this constructor is blocking, meaning that until whatever action in the queue that touches A is not completed, we will wait for all of them to complete before triggering a copy back from the device to the host. Whenever you have created one of these host accessors and it's made available, so after execution moves forward from this construction point that is blocking, the data that was on the device cannot be touched anymore. So meaning that, I mean, it's not guaranteed that there will be synchronization implicitly between what you do on the host and the device. So careful with that. So the other thing that we've done so far is that we use the fact that the destructor of a buffer object is also blocking and triggers a device to host copy. So all these opening a scope and closing a scope, what basically does is to update the data here that we initialize the buffer with. Yeah, so these are options for synchronization. We've been using this opening scope and closing scope everywhere in our buffer and accessor examples, and that's because it's very convenient. We don't need to remember to declare a host accessor. Of course, we will see later that it can be a kind of double-edged sword, but that's a discussion for tomorrow. Let's look at communication at the kernel level. So I've said that we have, if we use an ND range style parallel for kernel, that we have access to workgroup local memory, but we have not made any use of it in the previous example, in the previous exercise. Let's see how we can remedy that. So the ND range, recall again, we partition the execution space of the data parallel kernel into a global and local ranges. So the global range spans the whole execution range. So in the case of the matrix, before it was the full n by n, where n was the row and column dimension. Then the local range is a finer subdivision of this full execution range into smaller work groups. So we bunch some of the work items together in a work group. So each local range has its own bunch of work items, and work items in this work group have access to work group local memory, and that is achieved by using this local accessor type. So this type of accessor only has two template arguments. One is the type, and one is the dimension. So there is no read-write, write-only, read-only, and so on, because the local memory is always assumed to be a read-write. So this would map more or less to what in CUDA is shared memory, also called scratchpad memory. So one needs to be careful because even though, I mean, SYCL is supposed to be used across multiple kinds of devices, but this kind of local scratchpad memory is not always available on every kind of hardware. So for example, if you're using OpenMP, this is something that you don't have direct control over. So before going on and trying like writing all your code to use local memory, you should try to parameterize based on whether the device that you're trying to use actually has local memory or not, and you can get that kind of information with getinfo. So this is again an ND range. Now I'm showing in different colors all the different bunching of the work groups, and each of these different cubes of different color has access to its own workgroup local memory. So this resource, this memory is usually really small, so it's not something that you can rely on to hold a lot of stuff. So communication between work items in the same work groups is mandated by the standard. Communication between work items in different work groups, so trying for the green work group to communicate with the orange one will most likely result in a deadlock. So it's something that you should not rely upon. If it works, you might just be very lucky. So the workgroup local memory, it's only accessible once a workgroup as a whole starts execution. So this means that to construct this local accessor object, you need to be within a command group. So you need the handler object as one of the arguments. So it's not initialized when a workgroup starts execution, so you cannot rely on any value being there beforehand. So what you get is a scratch, so it might be trash. And once the workgroup finishes, it's done, so it does not persist. So you cannot rely on leaving stuff there when the workgroup finishes for the next workgroup. On top of this, these three as you wish limitations, or well, the way workgroup local memory is defined, on top of this, you need to synchronize between accesses to this scratchpad memory between within the same workgroup. What does this mean? It means that the local memory is not consistent, is not kept consistent by default, and this is to avoid an excessive performance hit when you write to this hardware resource. So to achieve synchronization, you call the barrier method on objects of item type such that each work item in the workgroup has the same view over the workgroup local memory. So if you are familiar with MPI programming, the concept of a barrier is not that much different from what happens in MPI. So when work items in the workgroup encounter the barrier, so you would call it item.barrier, they can only move past the barrier altogether. So that's essentially what a synchronization point would mean. So the first work item that gets to the barrier waits until all the work items in the work group reach the same point in the code, and then they move forward to the next commands to execute. So any work items that executes faster will have to wait a bit longer at the barrier for those work items that lag behind. So when do we use barriers? So whenever work items read from or write to local memory, then we need to put a barrier to make sure that whenever other items read to or read from or write to the same local memory, they have a consistent view of the memory. If we forget to add barriers, this leads either to race conditions or to very weird bugs where some items do not read the correct elements from the memory. So all of this to say that whenever you use workgroup local memory, you need to ensure as a programmer, this is something that the runtime cannot do for you. That the view of the memory is consistent within the workgroup, so that if you're saving stuff for work items to use, that all work items do have the same view of what you're saving there. So all of this introduction for the next exercise, where we still try to work on the matrix multiplication, but trying to further optimize a little bit. So we've seen that using work groups gives us better way of accessing memory that is not so wasteful, where we do multiple reads of the same stuff over and over again. Another further optimization is so-called tiling, where we use the fact that each row of A is reused multiple times to compute elements in the result array C. So if we can structure the local iteration range to work over smaller tiles, we can achieve better locality of the reads from memory. So each work item will compute an element in the result matrix C by loading a tile subsection of a row of A into workgroup local memory, and then taking that tile and multiplying it with an appropriately sized portion of the B matrix. And by appropriately sized portion, I mean something that has dimensions that are congruent with the size of the tile and with the number of columns of the B matrix. Here, since the tile is of size 4, we take a 4x4 subsection of B. So the result matrix we hold in global memory, and it's addressed through the global range or the ND range, while local memory accesses to the tile of A should be faster in principle, because the same little tile is reused multiple times. Okay, so this tries to do the same as before, but instead of loading the memory for reading A from global memory, it first loads it in local memory and then reuses it multiple times. So in principle, this is one of the suggested optimization strategies when you write GPU code, to use local memory to optimize reuses and basically load stuff in faster memory region. So of course, as I said, the trick here is to figure out when we should put a barrier when loading the tile and further writing to it and so on. So here is the description of the exercise, and as before, you can find it in this 04_tile mathmul folder. And if you want to skip directly to the solution, you're welcome to do so. So the last section for today, I think I went a bit long before, yeah. So but the last section for today is to look at an actual mini app. So this simple matrix multiplications, and try to port it from scratch, from a serial application to SYCL parallel. Before we move on to that, I just want to discuss a little bit the proposed solution for this tiled matrix multiplication, because I'm aware that it was probably a bit more challenging than the rest of the exercises we've had so far. So I just want to discuss a little bit how the proposed solution looks like and why. So of course, we first set up a queue, and then, as I said, not every device that can be available when we use a GPU selector might actually have a local memory. So here, put a little printout that will tell us whether we actually have real local memory, or is it an abstraction on top of global memory, and how large this local memory is. So for the devices that we have at hand, I've compiled, and I'm on one of the GPU nodes. It says that we actually have local memory, and this is of 48 kilobytes. So once we're beyond that, this exercise was a bit more general with respect to the other matrix multiplications, because it actually works for non-square matrices, as long as the A and B input matrices do have a common dimension. So the column dimension of A is the same as the row dimension of B. So here I just declare these two STD vectors of doubles with dimension m times k and k times n, so for A and B, and then I fill them as before with random numbers. Note that I don't declare the C, the output STD vector, because in this exercise, the suggested path to the solution also was using an host accessor, so that we don't just rely on the scoping rules to the job for us of copying back, but that we explicitly write down the host accessor. So once we have the input buffers filled on the host, we declare buffer objects to A and B, and also C. Okay, so for C, what to note is that we only declare it based on the range. So it's an n by n matrix, so we pass an n by n range, but it doesn't point to any already allocated memory. So this means that whenever we start using it, the runtime will know whether to perform an allocation on the device or the host, and when to do it and how to do it. So in our queue.submit, we have the lambda with the command group handler, and within this we have the accessors for A and B and C. So A and B we declare as read-only, and C we declare as read-write. So the comment here was also wrong. It's not supposed to be write-only, but it's read-write because we updated its contents, but we put the no init property because we don't care for whatever was there when the memory was reclaimed from the system. Then we declared the tile size. So the matrices here, even though this can work for rectangular matrices, I've declared them as square with size 256 times 256. So the tile size here, I choose this number 16. As a note, I said you can play around with other tile sizes, bigger, larger. It's important that the tile fits in local memory, because if it doesn't, then there's no point in using local memory at all, because it will probably fall back to using global memory. So once we have declared the tile size, we move forward and declare a tile. So I use auto here to not write the type myself. And the tile is a local accessor of type double 1. So it's one-dimensional tile. So it's just one little strip or one row with tile size 16 in the given command group handler. Now I declare global and local ranges. So the global range will span the whole output matrix n by n. So this is going to address the data in global memory, while the local range is one-dimensional because it's supposed to span the single tile, so the single strip in a row of the A matrix. So this is essentially 1D, but I still declare it as a two-dimensional range by giving it two arguments. So 1 comma tile size, meaning that I only am interested in the one row of A, but this row has to span tile size columns. Once I have the ranges defined, I can submit my parallel 4 with an ND range that takes the global and local ranges as arguments. Again, lambda accepting an ND item 2 as argument, and within this loop I do a few things. So the idea is that the matrix C and B will be accessed in global memory. Okay, and this is because we have to go through the whole of C, so it doesn't make sense to first load it in shared local memory and then copy it back to global memory. Will just work with its representation in global memory. And for B, because we're going to access the column, which are non-contiguous, so it doesn't really matter if we put a column in local memory or not, because anyway the access is going to be staggered. We get the M and N indices from the global ID of our item or ND item. And then for this I index, which is used to get a specific tile in the A matrix, so a single strip of one row of the A matrix, we use the local range, which is we built up to be able to address the tiles. So once we have the indices, we structure the loop as follows. We declare an accumulation variable, sum, which is basically the result that will go into one element of the C matrix. And then we loop over the inner index, which is common to A and B, okay? So we call this L, and this L goes all the way up to the size of the common index. But instead of doing a loop with one plus one increment, we do a tile-sized increment. So we load the whole tile and then process all of it, and then move to the next tile, in A, the next tile, and so on. So the first thing to do is to load what is actually in the in global memory for matrix A into the tile, which is in local memory. So this is the first thing we do. And then since all the items need to have a coherent view of the memory and consistent, and this is not guaranteed by the runtime, we call a barrier. So first we load from global memory to local memory, and then we synchronize so that the view of all the items of the local memory in the workgroup is the same. Now we have our tile loaded, and we can finally do a loop over the tile size to actually compute the value of the result, and we accumulate it into this sum variable. And once we're done, again, we need to synchronize because we need to make sure that all the reads from the tile are finished before we move forward with the next tile. Outside this loop, we update the value in the C matrix in this way. So we have the M and N indices in global memory. And the C matrix, the result is held in global memory. And we just change the value of this element at Mn to be the sum, to be the final result. How do we get C back from the device to the host? We declare a host accessor. As we said, this is a blocking constructor. So as long as the work here is not done, we will wait for it to be done before issuing a copy from device to the host. And now this C object is again an accessor, so we can index it with this notation with double subscript and check that value is actually correct, which this little loop is doing. So if I try to execute again, I see the printout from the probing of what kind of local memory I have, and then success means that the matrix multiplication was correct. Great. So let's move forward to the last section of today. Put in presentation mode. So this section presents a mini app that solves the heat equation for a 2D plate. So these materials was primarily developed by our colleagues at CSC. So they did provide us under MIT license the serial version of this mini app, and this is quite useful because it's an quite useful example of what you can, various steps that you can take to optimize a parallel port of a simple application. So what does this mini app do? So it tries to solve this partial differential equation in a two-dimensional spatial domain. So here we have U is the temperature field, the heat field, that is a function of the X and Y Cartesian direction in space and of time. And so what we want to solve is basically the time evolution of this heat field once we start at the given time equals 0 with certain conditions on the two-dimensional plate where we have an initial distribution of temperature. So how is this solved? So this is discretized both in time and space. The space discretization, we rewrite this Laplacian as a finite difference stencil. Here it's a 3-point stencil. So we need the value of the field at point ij, and there also its value at the adjacent points in the x and y direction. And for the time stepping, we take the given value at time step m, and then apply again a finite difference Euler scheme where we update it by multiplying the value of the Laplacian times the value of the time step. So this requires into D, so it's 5-point stencil. So to go from so the field at time step m, to the field at time step m plus 1. For any point, we need the value of the temperature field at itself and for other adjacent points, here represented with this little cross. So if we assume that we are discretizing over an 8x8 grid, we have to basically move the stencil around to obtain the updated value of the Laplacian at each of these points, and then applying the time step propagation. So there are some questions here about the number of arithmetic operations that one must do. So for every location and for every time step, there's 10 arithmetic operations we can see from the stencil, because we have 3 in each of the numerators, so that makes 6. And then there's 2 divisions and then the additions to get the update. So of course one can have you can have some back of the envelope calculations of how much arithmetic is involved, how many flops are involved in performing a certain number of time steps. We're not going to go through that at this point. I'm just trying to describe in general what this app is doing, which is necessary when we will go in and try to port it to SYCL. So as I've said, since we're applying a stencil, okay, and we're moving the stencil around, one needs to be careful when we are at the boundary of the 8x8 region that discretizes our plate, because if we want to apply the stencil here, there will be 2 points, these 2 red points, for which we don't have values. So we are kind of falling off the plate, and then the discretization wouldn't work. So you can have periodic boundary conditions, so basically making the plate fold on itself. But for this mini app, it's easier to just say that we put a buffer around that is always fixed temperature, is not time evolving, and that kind of relieves us from having kind of a complicated way of applying periodic boundary conditions. So this is what will happen in the code. So what you need to understand is that if we are discretizing over an nx times ny grid, so in this case 8x8, in reality we have 1 point extra in each direction to make sure that the application of the stencil doesn't just fall off the domain. So we are discretizing over nx times ny, but indeed we have nx plus 2, so 8 plus 2 elements in the x direction and 8 plus 2 elements in the y direction. So this is important. I'm remarking it because it's important when we're going to write the port to know how the size, for example, of the buffers and the ranges should be. So let's look for a moment at the source code. So the temperature field is represented by this field data structure, and the code for this is in day2/06 serial heat equation. So the field data structure is what represents U at any given time step. So the field knows the extent of the grid and what is the delta X and delta Y. So the size of each of the cells in the grid, and it holds the whole value. All the temperature values on the 2 grid are held inside this data structure as an STD vector. So the evolution data structure, the co-evolution operator, this is what computes the Laplacian for U. So it takes the current field and the previous field and the alpha value that multiplies the Laplacian, so the diffusion constant, and the time step. So this does the whole delta t times alpha times Laplacian and computes the Laplacian in this double loop, which is what is basically applying the 5-point stencil here into D. So, and for this, as I said, you need the given point and 2 points adjacent on the x-axis and 2 point adjacent on the y-axis. So this routine is the main computational routine, And this is called for a given number of time steps, which we can give as input arguments to the app. So yes, so we initialize the parameters, we initialize the initial conditions for the temperature field, and then set up the time step. So the time step we decide basically based on the space discretization, to make sure that we take time steps that do not lead to large error. And then we have the time evolution loop. So for each and every step, we apply the evolution operator and update the field. And the here there is a step missing. So we apply the time evolution. This little if checks whether we want to write the field as an image out. This is something that neat about this mini app that can be done. And after we've updated the values of the current field, we need to swap it with the previous field so that we can move forward to the next iteration and keep updating. So previous always contains the value of the field at the previous iteration, and current takes holds the value at the new iteration. So setup routines here do the allocation. So what I was saying, that if we are discretizing over nx and ny number of cells in each of the directions, we need to take into account that we have this buffer region around of red squares, so that we need to add 2 more in each of the directions to make sure that the stencil does not fall off and basically gives us a segmentation fault. So we can build this code and run it. So the app takes 3 parameters. So the size of the grid in each of the direction, 800 by 800 in this case, and how many time steps we should take. In this case, 1,000. And we can try out whether it works or not. So if you're following along as you should, you can go in your no, sorry, it was 0.5 for the serial one. So in the serial heat equation folder, this is fully complete, so we can configure and build. So this is serial, so there's no SYCL involved at the moment. And then we can call heat 800, 800, 1,000. And it will output an average time for the iterations and the temperature at the start, average temperature, and so on. Something helpful. So the initial boundary conditions, this is something that we do not need to care that much about. These are fixed. We are not going to try and change them. This is not the point of this exercise. So what is the point of this exercise after all? So we want to write a SYCL port. So we need to, whenever we are looking at the code that we want to port it to work on GPUs, there's a few questions that we should ask ourselves. So which kernel should we try to port first? So usually you have already a pretty good idea of what is taking most of the time in your application. And in this case, it's pretty evident that so the time evolution step is essentially serial, because we need to know what happened at the previous time step to get to the next. So this is a loop that we cannot parallelize because the execution of each step is not independent. However, the stencil application, so the evolve kernel, can be spread out over multiple workers. So this will be the target for our parallelization with SYCL. So we want to make sure that this double loop can execute more with higher performance, or rather on the GPU. We'll talk about performance a bit more tomorrow. So now that we know where we want to kind of what our direction of attack is, so looking at this evolve kernel, how do we fit the fact that we've chosen SYCL to provide a port to to write this code to run on GPU. So, and that essentially means how do we fit the abstractions that we've learned about, so the queue, the buffer, the accessor concepts, in a code base that already exists. So we're not writing this from scratch, we're just writing a port. So few aspects will need to be modified, of course, such that we can basically map the data as we have already laid out to these other abstractions. So, and this is basically what I would like you to do in the next 20 minutes. So here I've given some directions, some stuff that should help you in writing the port. So we can have breakout rooms for 20 minutes now, and after those 20 minutes, I'll try to go through the port that is already available. So if you want to look at the solution, just go in the 06 SYCL hit equation folder and, you know, try to compile it, try to run it, understanding what's happening. So before we leave for today, just want to say that either whether you managed or not to write a port, probably not, because the time was really short. You should have a look during this afternoon and see either through the solution and work it back how you can provide a port. The proposed solution uses buffers and accessors. And so I have both the serial version and the SYCL version compiled. What I want to show before leaving is that the SYCL version does run slower than the serial version. So there's definitely something that is going on that is not exactly as expected. So this is kind of on purpose because it sets us up to look at profiling, how to profile SYCL applications, and how to get information on where we're getting bad performance in our code tomorrow. So this is not supposed to be an optimal port, the one in the proposed solution. So don't worry, it's built to be that way. But make sure that you kind of understand within the solution what I'm trying to do with the code that I've written, and try to think where is that we are getting this bad performance. If you can think of anything that is already evident to you that could be done better. And then tomorrow we will try to confirm this suspicion using a profiler. So getting information from specialized tools and try to move forward with something that is more optimized. So this said, I think we can break up now and reconvene tomorrow. As usual in the HackMD, yes, Tur is opening the section. If you have quick feedback for today, please let us know. Stuff you like, stuff you didn't like. And because this helps us improve, and there's always something that I can quickly fix so that it's ready for tomorrow already. And then tomorrow I'll see you again at 9, and we will look at how to use subgroups, how to do profiling, and trade-offs of using buffer and accessors versus unified shared memory. That's all for today. So thanks for joining us.